what I'm interested in is the question of verification. So verification is big business in computer science. And the idea is simply, if you have a program, how do you know that it does what it's supposed to do? And so you might ask two different questions about this. Is it equivalent to its specification, whatever that means? And classically that's often undecidable because of the hobby. So you might ask something weaker, like does your program have some property that is desirable to you? Like you might want it to never hang, for example. And that might be decidable even though this is not. But I'm interested in the one-way model, so these are a little bit different. So the specification we're interested in for some one-way program will be quantum circuit. And for this talk I'm only interested in one property of is this one-way program deterministic? As in, can you show the outcome program does not depend on measuring outcomes? Now, at least for quantum computing, we're in a happy situation that this is at least a decidable problem. But on the other hand, if you have some not too complicated computational task, you might find that verifying this in a naive way is going to be completely infeasible. So what we're going to use here is a symbolic method, a formal language called ZX calculus, which is based on things that Bob was talking about yesterday. Now, to get started, I'm not going to talk about the one-way model just yet, but to try and introduce you to the calculus using quantum circuits. It's a bit simpler. So this is the syntax. So the objects in this calculus are graphs, and they have two kinds of vertices, red and green. And each vertex is annotated with an angle. And any way that you can plug these things together is a valid term in this language. Okay, and the collection of all such graphs forms a category, even a dagger compact category. You do not need to know these things. But here's the interpretation. So say I've got m incoming edges and n outgoing edges. Then the meaning of this green vertex will be that I'm going to take m copies of the zero state onto n copies of the zero state, and m copies of the one state onto n copies of the one state with the space of alpha. This is much easier to understand if you think of m equals 1, n equals 2, and alpha equals 0. You'll see this is just the one that copies the standard basis. And it's 0 goes to 2 copies of 0, 1 goes to 2 copies of 1. The red one is defined analogously, except now we're in the plus and minus basis. Okay, so this is again a copying operation for the standard basis, a copying operation for the plus and minus basis with some phase shift. Okay, so let's try and write down some simple things so we can get hang of this. So if my angle is 0, I'm not going to write it, I'm just going to miss it off. So 0 turns out to be 0 cubed, if it's in red. If I had an angle of pi here, this would be the 1. And similarly, in the green, if I have no angle, I just have 0. This is the plus state. And if I have pi, then this will be the minus state. So that's what, notice I have nothing coming in and one thing coming out. So this is going to be the preparation of a fresh qubit. If it was the other way up, it would be a projection. Now if I have one in and one out, so this is a map from qubits to qubits. This is just going to be your z rotation, and this will be your x rotation. And the special case for alpha and beta are pi, we get the boundary matrices. Okay, so these are 1 qubit gates. I can look now at the C0, and it turns out that you can compute what the meaning of this thing is just by composing the linear maps you get from these things. And these turn out to be the same, and they turn out to give you the C0. So in general, I'm going to write this bar horizontally here. It doesn't matter which way up it goes. Okay, so I have x rotations, z rotations, and C0. So I already know that I can write down any quantum circuit in this language. That on its own is maybe not that interesting because circuits might have more than one presentation that are actually giving you the same circuit. So I'm now going to impose some equations in this language. And some of these you will be remembering from Bob's talk. So this is the thing that Bob's talking about spiders, right? So these dots are the spiders of Bob's talk. These are the non-exploding kind. And when I have two dots of the same color next to each other, I can combine them and I add the angles. If I have loops, I can remove them. And if I have one in, one out, annotated with 0, I can just drop this vertex. Now these three together are what Bob called the spider rule. Here we have some properties of the things annotated with pi. Because these are Pauli's, they can commute through these dots at the cost of flipping the phase. So if I have one coming in here, many coming out, so that the Pauli just goes through, I get many copies of Pauli and I flip the phase. I have some more equations. So this one is what Bob called complementarity. This is some statement essentially that these things form a Hopf algebra. In fact, they also form a bi-algebra. So we have this equation, and we have this rule that says if I have a state here, it'll be copied. Now remember that this is only copied the 0 and 1 basis, and this is the qubit 0, so we ought to have this rule. This thing at the bottom is unintuitive and complicated. I'll explain it a little bit later. But what does it say here? I have a green dot, and it's surrounded by red dots with pi by 2 phase, and the phase here is some angle plus n times pi by 2, where n is the number of these things. Then I'm allowed to change the colors. So this will become red, these will become green minus pi by 2, and this extra factor here will go away. So I have all these equations, and then it turns out that they're all sound in the sense that whenever I draw two diagrams, and by doing these rewrite rules, I can get from one to the other. They have the same denotation as linear maps. So let's see what we can do with this. Here's my C0 again. How can I convince you symbolically that it's a C0? Well, this is my control qubit, this is my target qubit. So I'm going to feed it qubit 1 and see what happens. So by these two rules, I'm allowed to commute this pi with the green dot. And then using my spider rule, that copy of the pi joins on here. So now we have the control qubit passed through unchanged, and now I'm acting as a Pauli X on the target qubit. I think Alex already showed you this example. Right, so I'll do it fast. These terms are graphs. So you can do any deformation you want with topology. It's just the same as a graph, it's the same. So I push this twist through and you see here that I have this bi-algebra configuration turned on its side. So I can do a rewrite there. And then I can use my spider rule twice, once for red and once for green. Do this. I have my Hopf rule. So I can remove those. And again, by this rule, I can get rid of those two bits. So 3 C0 gives you the spin. Something that's going to be important later on in the talk is the Hadamard. So this is what it looks like. If you compute the Euler decomposition of Hadamard, it's this. So I'm going to introduce a new symbol into my language for H, because it's going to be more convenient later on. But now that I have that, I can have the following rule. If I have a green dot, and I surround it by H, then I just unpack the definition, I get this, which is the weird configuration of my color changing rule. So I can change the colors. I have pi by 2 next to minus pi by 2 and all of those legs, so they go away. So now you see there's total symmetry between the green part of calculus and the red part of calculus. So anything I show you the colors one way around is also true with colors flipped. Okay. So let's use this Hadamard for something. Here's the C0 again. So I want a CZ, I know that I just have to put Hadamards onto the target qubit. And using my color changing rule, I can replace it with this. Yeah. So now you can immediately read from this picture a very simple property of this Hadamard, and it's symmetric in its inputs. Because the picture is symmetric. And we can do some other toy examples, like let's square the CZ. So use a spider, use the color changing rule. Hadamard, you can prove that Hadamard squares to 0 from this definition. So that goes away. Optional, that goes away. Those go away. Those go away. Okay, so simple computations we can do like this. Now, obviously, not every graph I write down is going to correspond to a quantum circuit. I can write down all kinds of crazy stuff, which will not be circuits. Will not have the right arity, will not give unitary denotation. So we need a criteria to recognize which diagrams are circuits. And this is what this definition is. So it's a little bit long, but it's actually relatively clear once you read it. So I want to put a path covering on the diagram. It's going to cover all of the vertices. And each path should be disjoint from all the others. So it should cover all of these vertices. And I want, if the graph contains a cycle, then at least one of the edges that traverses in the cycle must go against the direction of at least one of the paths. So this is a causality condition, right? So you don't have loops in your circuit. And this last thing is just a technical thing to stop degenerate things creeping in. Right? So don't worry about that. Okay, so for example, how about this one? Is it a circuit? Yes. Okay, so this is the path covering. So this one doesn't have to be covered. This is H, and these vertices are covered by this, and this vertex covered here. So all my paths have to end in an output. And you can see that this is a circuit, because if I use my spider rule backwards, I get this. So you see it's an ancillary qubit, then a C0, then a CZ. This one, on the other hand, is not a circuit because there's no path covering that can avoid this cycle. Okay, so it's not going to work. And then you have a theorem that says that if the diagram is circuit-like, then its denotation, its interpretation as a linear map, will be unitary embedded. Basically, this means because you are a circuit with some number of ancillary. Okay. So this is which diagrams are circuits. So I'm going to try and view the one-way computer in a sort of circuit-like way. Now, I'm a little bit embarrassed, first of all, because I flagrantly stole this picture from Robert Rossendorf. And secondly, to try and explain the one-way model to a room full of people who know it much better than I do. But for the benefit of those of you who don't know it, here's how it works. You have some large array of qubits initialized in this plus state, and then you apply CZ operations to entangle them all in some specified graph. Now, since we want to have an input, we'll have also some input qubits, which will again be coupled into the graph with CZ. And then all that happens now that now that we've created this big entangled state, is we do 1 qubit measurements in this basis. So this is just a rotated Z basis. Okay, so when you measure a qubit, obviously it's disentangled from the cluster, and depending which outcome you saw, will change the state of the remaining cluster. So you just go through the whole thing until you're left with some output qubits, and then you say, okay, I may now do some Pauli corrections on these guys. So you're only ever doing 1 qubit operations on the cluster. Now the point is that as I'm doing these 1 qubit measurements, I have 2 outcomes. I have the good outcome and the bad outcome. What I'm hoping is if I go down this path of all yay, then I'm going to compute the thing that I wanted to compute. And the question is, suppose that I see boo at some place, is there still some changes I can make to the measurements I haven't done yet to mean that I'll compute the same thing as if I went down this path? Okay? So the idea is that you modify the later measurements taking into account the results of the earlier measurements. So the question is, can this be done deterministically? Okay. So more formally, we're going to define one-way programs using this measurement calculus, which is due to Fedor-Kashef and Panagan. And this is the syntax. So a program in this language is a string of these commands. So we have n means make a new qubit in the plus state. EIJ means entangle qubits I and j. Here we're going to measure qubit I with the angle alpha, And these two things, S and T, are classical flags, classical bits, that will modify this angle. Now the idea being that these guys encode the results of some earlier measurements. So this is how you take into account the earlier results in the later part of the program. And you can apply Pauli's on qubit I dependent on Simpson. Okay, and there's a nice standardization theorem that says that whenever I write a program in this language, it's always equivalent to one where the commands occur in this order. So I'm just going to always assume that they're in that order. So here's a little example of how this will look in the calculus. Here are all my plus states that I prepared. Here's my input. Here's my entangling operations, so they're just being entangled in a chain here. And here are my projected measurements. Well, notice these are projections, not measurements, right? This is just a projection. I will show you the measurements properly in a minute. But the idea being now, as Alex demonstrated with Quantomatic yesterday, is that everything you see is green. So they can all go together, and I can start removing things, and I can cancel those, and I can change this color, and I can cancel those. So that's a 1 qubit entry given by its Euler decomposition. So essentially I proved that up to non-determinism, because I ignored the measurements, that measurement-based thing that I showed you conforms to its specification. Okay, so let's deal with measurements then. So suppose I've got some measuring device for the standard basis. What I want to view is not to have these two possibilities here, but instead to use a projection and then have this Pauli here, in the presence or absence of the Pauli, is telling you what measurement outcome occurred. And this will just be replaced by projection. So what I actually want to measure this basis, and in my syntax, this is the Pauli Z, and the measuring device now is just the projections. Right? So that's what a measurement looks like. Okay, so here's a little example. Here's the qubit, here's the CZ gate, and here's my measurement. This is with angle 0. So if I see the yay outcome, I get this. Okay, yay. So that all collapses, those go away. I see this program computes the Hadamard. But if I see the boo outcome, I have this pi here. And so that has to come through, and it will pass through the Hadamard. And if I want this program to be deterministic, now I know that I must do a correction at the end with Pauli X. Okay, so I'm going to modify the syntax of the language slightly to incorporate this idea of conditionality. So I'm going to take some set of formal variables, S, and on each of my colored vertices, I'm going to, as well as the angle, have some collection of these variables. In fact, in the examples I'll show you, this will always just be one variable. And the intended interpretation of this is that whenever I have a valuation of those variables, i.e. a function from S into 0, 1, then I'll define a new diagram by either at each vertex, when I have this collection of variables there, I'll form the sum modulo 2, and if it's 0, then I will replace the angle alpha with 0, and if it's 1, I'll leave alpha unchanged. Okay, so now I've got, for every diagram, if I do n conditional operations in it, I've now got 2 to the n diagrams, which will all be unitary embeddings. And this is giving me the branches of my computation. So, and that allows me to define a CP map, which will do the same thing as what this program will do. So the simplest example is this one. Okay, so we're going to measure in the plus minus basis. So this is my projection on 0. And here's a conditional operation, a Pauli flip with some variable x. And what x is telling you is the result of this measurement. So if x is 0, this Pauli flip goes away. You just have this. If x is 1, you keep it. And you get the semantics down here. So I'm going to see that I have the 2 possible branches of my measurement. I change the syntax, so I go back and I put these variables back into all the equational rules. Everything's essentially the same, except that In some cases, most cases, you have to make sure that you have the same variables whenever you do some rule like this. But in some cases like this one, these can commute because this rule will be true in every valuation. But these are otherwise the same equations, except I put the H rules in here explicitly because I'm going to use H as a symbol now. Okay. So now we can translate any measurement calculus pattern into the ZX calculus. So my new qubit is just this green guy, my entangling gate is the CZ gate like I showed you, here's the measurement, and here are the conditional patterns. It's worth noticing here that the status of these variables is not the same in both places. So here you want to think of this value I as being determined by this measurement, whereas here it's conditional. So it's implied, there's no real causality in here, it's just implied that these things will correlate. And this means that you can actually write down wildly unphysical things using this notation. So you just have to avoid doing that. Alright, so here's an example. This is the C0 gate, and this is the pattern. Now, the question you should be asking is, how on earth am I supposed to know that's a C0 gate? Okay, and it's not very obvious. This is the diagram that you get by just translating this syntax into the ZX calculus. But now I have my equations, so I can do something with this. So from here to here, basically all that's happening is all the green dots are being collapsed together whenever they can be. And now I'm going to start pulling through these conditional operations. And see, okay, that's right. Some of these, like here, so this is been introduced by the measurement of qubit 2. So I have 2 here. Over here, I have Pauli conditional on 2. So what I want to happen is that all of the error terms introduced by the measurement should somehow meet up with all these correcting terms and cancel them all out. And that is what will happen. So I just push these all through the graph. Right. So this one, it comes through here, and it becomes red. And now I have pi and pi, both of the same variable, so those will cancel out there here. And you proceed in the same way, and you get to this nice picture, which is C0. And most importantly, it has no conditional operations in it, so you know that it's deterministic. Okay, so the question is, can we do this in general? And thanks to theorems by Dan, Simon Perry, Medimala, I forgot someone. No, okay. We know at least sufficient conditions for this kind of thing. So now I'm going to try and get a bit more into the analysis of determinism and flow using these languages. So let's sort of reset where we're at. So we have this measurement pattern, this program, very basic, low-level syntax. But every measurement pattern has an underlying geometry, which is basically the graph state you built your pattern on top of. And if you have a graph state or a geometry, there's some graph theoretic conditions called flow and G-flow respectively, which tell you that if you have these properties, one, you can do something deterministic with this graph state, and two, it actually tells you where you must put the corrections. Okay, so if you have all of these things, then you get a uniformly deterministic pattern. Uniformly means it doesn't matter what the angles and the measurements are. But the thing to note is these guys are not necessarily the same pattern, right? Because this one has told you where you had to put the corrections, but you already put them in this one. So you would quite like to be sure that the thing you actually wrote is deterministic, not just you could have written something deterministic, but you screwed it up. Okay, and once you have this uniformly deterministic pattern, you can get a quantum circuit from it. And in the case of the G-flow, well, apart from what I'm going to tell you today, you would usually have ancilla qubits. In fact, because of what I'm going to show you, that's not the case. You don't need ancilla qubits. Okay, so this is how it's going to go. I already showed you this translation, measurement pattern into ZX calculus. But you can also go a more roundabout route starting from the geometry and sort of having the geometry annotated with measurements, which will be simpler than this. But there will always be a rewriting relation between these two things. Now, if it turns out that I have flow, then I'm going to have some rewrite strategy here for pushing all those corrections through the circuit, like I told you. And if the original pattern was deterministic, this would be a circuit-like diagram with no conditional operations. In the case that it doesn't have flow, but it has G-flow, then I'll have some other rewrite strategy which is going to give me something that has flow, and then I can do the first thing. Okay, so here's the same pattern again. What is the geometry? So you look here at the entangling gates. So you see 1 to 3, 2 to 3, 3 to 4. So you have a graph like this. The vertices are the qubits, the edges are the entangling gates. Because 3 and 4 are fresh qubits, that means 1 and 2 are inputs. So I know 1 and 2. And because 2 and 3 were measured, I know that 1 and 4 are outputs. So this triple, the graph, the inputs and the outputs, is the geometry. Okay, so let GIO be a geometry. The thing we want to talk about is a thing called the flow, which is a pair of a function and a partial order. The function assigns to every measured qubit a successor. And we require that the successor be connected to the qubit that it's a successor of. We require that the successor be after the measured qubit in this partial order. And we say that all the neighbors of this guy must also be after U. Right? So what you learn here is f of U is the qubit where you must correct the error that you saw when you measured U. Okay, and the theorem is that if your geometry has flow, then there exists uniformity determinism pattern. Let's have a look at this in a little bit more detail. So here is a geometry. And I'll go look at this qubit V. So if I measure V and I see the wrong answer, what the flow tells me is I go to f of V and I do a Pauli there and I correct for that. Okay? And you iterate f and you find you have a disjoint set of paths from the inputs to the outputs. Okay, so I can go directly from the geometry, here's the geometry, this is the C01 again, to a pattern. Now you can see how you do it. I make all the vertices here into green dots, and on all the edges I put an H. And if it's an input, I put some lines coming in. If it's an output, I put some lines going out. Okay, so I'm going to call this this diagram D of P, where P is the pattern. Okay, and the theorem now says that if the geometry has a flow, then this diagram is circuit-like, or at least equivalent to a circuit-like diagram. And it's kind of obvious from this picture, right? These are the paths of my path covering, and my causality condition is essentially the same thing as the partial order. Right. Okay. So I have the diagram from a pattern which I made from the syntax. I have this diagram that I made from the geometry. How are they related? Well, I can construct a new diagram by taking in the pattern based on my geometry at all the interior vertices and just sticking on the appropriate measurement if this was a measured qubit. If this was an output qubit, then I might have to stick on some correctors, depending on what was in the original pattern. But this is completely mechanical. And the interesting point is that the diagram you get from the syntax will rewrite to this diagram that you made out of the geometry. That means then, that if I'm doing rewrites on the geometry, as long as I don't erase these qubits, these vertices, then I can do all kinds of rewrites in the geometry, stick back on my measurements, and I'm still still working with the same object. Okay, so suppose we've got the flow. What's the idea now? So I'll have some conditional operation, and the flow will tell it how it must traverse through the graph. Okay, so these are some rules, but here's just an example. So here's my pattern. Here is the flow, and somehow these conditional operations and measurement operations have to be eliminated. So we'll start here, and he'll be pulled onto this flow. And you'll see that it goes, so it just goes through there, goes past 8 to change its colour. Now you should be copied, so I have 2 of them. And these will cancel out. And then that other one can proceed through by iteration here. And then this one, once I join them back onto here, I've now got circuit-like diagram with no conditional operations in it. So this is deterministic, and this is the specification. More generally, right, look at this one. So I have my qubit I here, and this is the qubit f of I, its successor according to the flow. These little boxes just mean either an output or a measurement. I don't want to say what it is. So here's qubit I being measured. This is the error term corresponding to this measurement. So it's going to follow the flow. So it comes down here, and it becomes Pauli X. So now it wants to go through this copier. So it goes through the copier, it gets copied. Now I have, at the measurement of f of I have this X. And I also have these guys. If I push them through, I find they come through, they become Pauli Zs. And then I can, but I don't have to, then I put them onto the measurements of all the neighbours of f of I. Right? So these are all the neighbours of f of I. And so what this is telling me is to correct it qubit I in error, you do an X at f of I, and you do a Z at all the neighbours of f of I. And in principle, these Zs could actually go somewhere else, but I don't know the graph structure here, so I can't say anything. So this is giving you the uniformly deterministic pattern that you get from the flow theory. And you know that you can't do any better because these you can't commute a Pauli past an arbitrary angle unless this angle is 0 or pi. So this is the best you can do for uniformity. And so this is basically a graphical proof of the original flow theory. The point being that I do all this, and then I'm going to terminate in the state where either I removed all the operations, or I didn't. If I removed them all, I'm deterministic, great. If I didn't, they're stuck at some point in the graph. That point where they get stuck is a qubit in the original pattern. It tells me I should put a correction there, and not some other place. Okay, so by doing this process, you've effectively debugged your original pattern. Okay, I'm running a bit short of time, so I'm not going to go into the G-flow strategy in any great detail. But here is the idea. So the generalized flow is, instead of having one correcting qubit, you have a set of correcting qubits. And the theorem, Brown, Kashefi, Mala, and Pedri says that if the geometry has a generalized flow, if and only if it has a stepwise, strongly uniformly deterministic pattern. So strongly means all the branches are equal, stepwise means you can correct it one step. Okay, and then Simon and I proved in 2010 that if a geometry has, this should be G-flow, not flow. If a geometry has G-flow, then you can rewrite the corresponding diagram to a circuit-like diagram. Okay, this is the definition of G-flow. So instead of having this G function now, which picks out a set of correcting qubits, you have again this partial order giving you some causality conditions. And instead of, what you want is that the correcting set of qubits sees the error oddly and the past evenly. So instead of this, so you can't introduce any new errors into the past by doing this. Don't worry about it. Okay, that's what I said. So let's look back at our graph state. This is what it looks like when I first draw it. But usually I can do something like this, where I make some of the vertices red by pulling these edges out. Okay, that's going to be very helpful in a second. So I want you to remember this rule. I say I have a Hopf algebra with a trivial antipode, so I can make this rewrite. But Hopf algebras have a normal form theorem that says I'll have any old mess like this, I can always replace it with something of this form, where all the green dots are on one side talking to all the red dots. And what's preserved here is a number of paths from here to here, here to here, and so on. So in particular, if I have something with a relatively nice shape like this, I can transform it to something with a horrible shape like this. So with this idea, I can make the following definition, which is complicated. But the idea is this. I've got some two-colored this bipartite graph like this, the connections, whatever they are, and I can rewrite it to something with this shape. So this is my normal form, and I'm rewriting it to something worse. But the nice thing about this is it has a particular structure where it has a very precise number of paths going through it, right? And by, so the idea is that I can use this new lemma, so to rewrite my circuit with G-flow, my pattern with G-flow into something with flow. So here's B2. The correcting set of B2 is all of these guys. So I use my lemma, and now I have a different correcting set, and in particular, all the correctors, they only have one corrector. So this is just a flow. Locally, it's just a flow. I can do the same here. The correcting set of A0 is these two guys. I use my lemma again, I get this, and again it has a flow, not a G-flow. So the diagram is getting taller, but narrow. And it terminates in the situation where you have a flow. And now that I've transformed my geometry, I've simplified a bit because these are not all required. So I introduce all these extra vertices here, which are annotated with 0 and 1 and 1 out, so they can all go. I retain my original vertices. I've transformed my geometry from the G-flow geometry to flow geometry. I can stick my measurements back on and do the stuff that I said earlier. And what is particularly nice about this is that somehow having this Hopf algebra structure around is telling you that you can take these delocalized corrections you have to do in the G-flow and somehow sequentialize them into one particular place. Okay, and the last thing I want to mention is, because the theorems about flow and G-flow, they're about uniform determinism. So it should work for any choice of angles. But there are some cases where you get determinism which isn't uniform. And at least in these cases, for example here, this measurement is 0. And because it's 0, I can do this rewrite here, and this whole bit just falls off. And you can see that this is now deterministic. So you can, because you have the actual pattern and not some generalization of the pattern, you can verify things non-uniform. Okay, thank you very much.
Questions? Just wondering, if you was given an arbitrary layout, what's the complexity of deciding across these two modes?
I have no idea.